Okay, good morning all, and welcome to the inaugural meeting of our OCP High Performance Compute Interconnect work group. Thanks for the good attendance. It was good to see and all the new faces as well, actually. So that's great. So today I've got a few slides that I want to go through, and just to sort of set the scene. I'm thinking maybe it's worth me going through to set the full picture before we start diving down into so I'll try and do that quite quickly, and then we'll go back to the slides and we can start doing discussions around the different topics. So I'd rather give you the big picture rather than us get locked in the weeds of the of one particular topic and then spend all the meeting on that. Okay, so that's going to be what the approach I'm going to take. There are also some procedural things I'd like to get going with this work group. I would like to not be the one leading it. It's pretty tough leading the other one, and I definitely want to be a participant, but I think somebody in the interconnect field could be the lead of the group, and maybe depending if we have separate investigations going on, individuals can take different leads from the various pieces. So basically I'm looking for volunteers to help out here, and that'll be good as we ramp this up, because there's going to be a lot of work going on in lots of different disciplines. So so on that note, what I'd like to first do is for us to go through introductions, please, and I'll just take some brief notes on the introductions. Plus, by the way, we are recording this, and there is an AI feature that allows you to summarize. It says stop summary, so it looks like maybe it is running a summary, Scott. Okay, I need to investigate that. I'll investigate that. AI companion, there we go, AI companion. No. Anyway, I'll investigate the AI features, but it can do a summary of the meeting, which is quite nice. The wonders of these large language models. Okay, so let's start. I'll just go around as they appear on my screen. So Mike Felton, would you mind giving just a quick introduction, who you are, what's your company, and your interest in joining us?
Yeah, thanks, Alan. I think we met once before. I'm Mick Felton, work for ASUS. We build cables, connectors, cages, designs, plug assemblies, high-speed stuff. Been working here for 5 years. I'm the director of engineering. And before this, I used to work at Dell EMC.
Okay, yeah, Mick, welcome aboard. Thank you. Next, well, myself, I'm Alan Cantle, and my background, I'm a double E. I'm known for FPGA computing, being a pioneer in that area, and I've been the OCP High Performance Compute Sub-Project technical lead for the last more than two and a half years, maybe coming on 3 now, actually. We're driving this sort of radical initiative of re-architecting computing, or redefining compute architecture from the ground up. So next, Michael Choi.
Hi, this is Michael from Samsung. Yeah, I'm dealing with the CXL standardization in Samsung, and then I'm actually put my effort on the CXL-based memory pooling sharing solution for futuristic data center and HPC. So yeah, my background is in the data center, the acceleration with the XPU, like CPU, GPU, FPGA, MPU, APU, whatever, right? And then among that, acceleration cluster, I think the memory and the storage, will take great role. So right now the CXL technology is arrived, and then we can actually achieve, even memory as a disaggregated resource in the data center. So that's what I'm working on and try to change, the data center environment with the CXL. Yeah, that's
Thank you.
it from me.
Thank you. Al Ford.
Yep. Good morning, everyone. I'm Al Ford. I'm currently unemployed, but I've had a 25-year career in IT. Also similar to Mick. One of my recent roles was at Dell Technologies, where I was an artificial intelligence alliances manager. So I've had a long technical background, but my goal now is to help some of the larger HPC customers consider and hopefully make the transition to HPC modular capabilities.
Thank you. Welcome aboard. Next, Mitch. You're on mute.
Sorry. Yeah, I got it. Yeah, Mitch Wright, representing Liquid. And Liquid is a composable today PCI Express, and I lead the CXL architecture lead going forward. My legacy is been in the CXL ecosystem for the last couple of years, but 23 years in the ProLiant server organization at HPE.
Thank you, Mitch. And then we got Kevin Cameron.
Yeah, hi. I'm Kevin Cameron. I work in EDA. I'm interested in the tool side of building these systems, simulation and that kind of thing.
Okay, thank you. Jinhua Chen.
Yeah, this is Jinhua. I'm the CTO of Luxia Technology. I've been Luxia for 10 years. Luxia is an interconnect company making high-speed cables and the connectors. Before joining Luxia, I was in TE for 3 years and as an engineering director. And before that, I worked with Mick in EMC for 10 years as I managed an SI team. I think, Alan, we met in OCP, and I'm really surprised by your work and need a lot of interconnect. That's why I'm joining here. Hope we can contribute.
Great, yeah, well, great to meet you there, and thank you for coming along.
Yep.
Next is Zinen Fang. I'm not sure if I'm pronouncing your name right. Apologies.
Yeah, thank you, Alan. Yeah, that's good enough. So a lot of people call me Z, so it's easier.
Okay, Z. Okay, that's it.
Yeah, so I'm a technologist from Amphenol. I sit in different committees for Amphenol, act as Amphenol representative for the industry standard development. And I help our team in the product development and product roadmap definition. I have multiple year product development experience in cable connect side.
Okay, brilliant. Thank you. Okay, and then next is Elang Chen.
Elang Chen from Lenovo CSP team. We work with the customer for the data center solution.
Okay, thank you. Kyle Salmon.
Yeah, I'm Kyle. I'm here representing DE Connectivity. Folks know we make connectors and cables both in the box and out of the box. I sit on our smart architecture team and I'm active in OCP NIC and various other standards. So yeah, they represent DE today.
Okay, great. Welcome on. Gregory Selman.
Hey, this is Greg Selman. I am an architect at AMD, as well as the server project steering committee lead for OCP. Interested to see where this goes, what types of interconnects are being used, and particularly where we can take CXL.
Great, welcome aboard. Thank you. Xin Wu.
Good morning. Xing Wu here, and I'm with Source Photonics. We are interested in potential applications on the optics interconnect for CXL and high performance computing. Thank you.
Welcome aboard, Zin. Sorry, which photonics company? Sorry, I missed that.
Source Photonics.
Could you pop that in? How do you spell that?
Yeah, Source.
Source Photonics. Ah, right. I got you. Thank you.
Thank you.
And Carl Wan. Oh, it's another chap from Luxor. Welcome. Did you manage to dial in? Did you introduce?
Seems like he did. Yeah. Carl, introduce yourself.
Okay, hello everyone. This is Carl from Luxor. I'm the product manager and the marketing manager of connector and cables. Very glad to be here. Thank you.
Great, welcome aboard. Right. Okay, well, let me just capture you as well there in my. Okay, right, let me switch over to the presentation. So I'll share my screen. I'll share my primary screen. Okay, I'll put that in display mode. Can you all see that?
Yes.
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 Okay, great. So like I said, let me just quickly flick through this to give everybody a background and get everyone up to speed. There's quite a few new people that haven't seen the previous stuff. So the first thing we have, just for those of you that don't know, we do have a bi-weekly meeting for the entire OCP HPC sub-project. And we've been working on concepts for pretty much 2 to 3 years now. And you're seeing a picture of the core module. You will see it's very OAM-like. It's inspired by OAM, but you will see that on the back there's a bunch of connectors. There's not the mezzanine connector if you're familiar with OAM standard. That's because we don't have a motherboard. Everything is either directly plugged in a backplane type format, or cabled when you're connecting between modules. So the idea is that, and it's all direct water cooled, which we're not worried about that here right now. That is another work group that I'm going to be setting up shortly. So the topics that I want to really discuss around the challenges we have to address with this modular approach is, first of all, we need to remove through-hole features from all the connectors we use. So that's a critical thing. I'll show you why. Then we leverage the EDSFF interconnect, specifically the 4C and 4C plus connectors. And so we'll take a closer look at what we're doing with them and the tweaks we might need to help us out there. Then I'll look at the topology interconnect. So that's the smaller connectors you saw. That's sort of cabling between modules. So that what solution do we go with there? And finally, we'll look at the E3S module and active cabling thermal interconnect. We have everything is actually directly water cooled or conductively cooled to a water channel. And so I'm hoping the interconnect experts can actually help us out on a thermal connector. We'll get into that details. And there is a fifth item, which is other, which I'll cover a few other things that I've not gone into any detail on, but we should be thinking of. So removing through-hole features from the connectors. So in the top right-hand corner, you can see the connectors from the module that you saw on the first slide, just the back sides of the ball, and you can see all of the through-hole features on those connectors that I've got on the card today. Basically, there's 147 holes in the board for these connectors to hold them mechanically down. So because this is such a dense with components on the both sides of the board, those through holes are going to clash with the top side components, and they're pretty much going to make the PCB fairly unroutable or a lot less routable. So we really want to be able to get rid of those all through-hole features on these connectors. So is 100% surface mount possible is the question. Maybe we need an alignment frame instead of the pips, where we could maybe align all these connectors, so when they're actually put through reflow, that they have a level of placement precision that we need. And we're going to need some other mechanical rigidity mechanisms in place so we don't tear these connectors off the boards. But we want a bit more of but we can have some surface mount mechanical help, but we need to rely on other mechanisms for that. I've done a zoom in of the two connectors. That one there is a 4C being shown, the long one, and the short one is the current PCI SIG MCIO connector being shown there. Then, but on the topology interconnect, I just did show the MCIO one in the solution, but basically, I'm starting to think we possibly want a connector of our own, or leverage an existing connector that can maybe serve our purposes. So what I've investigated so far on this module standard, or what we've investigated so far in this module standard, is obviously the PCI SIG MCIO. That's a CXL in PCIe going forward. That's at 32 gig NRZ right now, and I think there's a pathway with this connector to 64 gig PAM4. The Samtec Accelerate interconnect is good for doing bypass at the 112 gig PAM4 for Ethernet type connections. And I'm not sure if there's a roadmap to 224 with this one or not. And Molex have a near stack interconnect solution that also, I believe, is 112 gig PAM4, and I'm not sure whether that's going up to the 224. So this is the ones that we've looked at. I think the speed part of the equation here, and the way these connectors and cables are manufactured to achieve these speeds, are an interesting an interesting point. But to get to the specifics, the bullet points on the left, what we want out of this is this module standard is protocol agnostic. We don't care whether it's NVLink, Infinity Fabric, PCI, Ethernet. We want to be able to cover all of the bases effectively with this interconnect. This is a mechanical and electrical module that gives us compatibility in the physical standard, and protocols, etc., dictated by the silicon that gets put onto these modules. We don't want to dictate that in the module standard. So therefore, we have this horrible clash of impedance issues that you guys in the connector world have known forever. PCI went down the route of 85 ohms away from where Ethernet was 100. They tried to, or we split the difference with connectors being 92, but I'm not sure if that really helps signal integrity at these as we traverse these higher speeds. And I do understand that maybe Ethernet is already moved to 92 to play their half of the deal, but I don't see Intel and PCI SIG anytime soon moving to 92 with PCI, sadly. So you know, we're still going to have some level of impedance considerations here, and we need to think about that from a signal integrity perspective. Then in terms of lanes, we've chosen to standardize on it by 8-lane for transceivers. It's certainly like it to go at least up to 112 gig electrical before, you know, and you know, before we switch to this optical world. But if we can get it to 224, then that's great. So that's a question mark. Sidebands. We want to move. We really do need sidebands because the way this module is going to work is it's going to power up the BMC, the system manager, and actually discover what's plugged in. And you know, there's a number of other work groups within OCP that are working on this, like CMS is composable memory systems, trying to discover the memory network. So we need to do that. I personally believe that, you know, we've been stuck in the 1970s with sideband management, and I want to get over that, and let's escape that properly. LTPI is I2C and I3C tunneling over LVDS basically, and so I would like to sort of simplify the sidebands to just one differential pair transmit and one receive, and maybe we can integrate the clocks into that, or maybe we have separate differential pairs for the clocks. I need some SI and chip experts on that, whether we can consolidate those two together or not. And then we've the cable. I think we just need a cable present pin. So in a discovery of a network, we actually know that a connector appears to be plugged in. So if it doesn't seem to go anywhere, we can flag a warning on that. So just less sidebands than we're used to on these PCI, for example. More sidebands than, well, we don't get any sidebands on Ethernet. Okay, so we've got that sort of sitting in between the two. We also want to support active cables for chiplet retimers and near packaged optics, silicon photonics. I'm targeting, I think 5 watts should be a good figure for us to, and hopefully that will improve as our picojoules per bit of silicon photonics in the lights comes down. But I'm hoping we can target around 5 watts for the active cables. Again, they will be actively cooled, water cooled. We need a 12-volt power pin for that, and and we need paddle card support for the active components. And of the 3 connectors on the right, natively only MCIO supports a paddle card approach, mainly because both Samtec's Accelerate and Molex's NearStack have gone to wire straight to pin. They actually solder the twin axe wire straight onto the pin for a good SI path. And so I'm wondering if we can do both of these, and I have some ideas in cartoon PowerPoint form, and that's where I'm thinking we need to innovate on the connector design here, so that we can get down to one connector that serves all purposes. The total number of pins based on that is about 66 pins. I just did this slide. I quickly threw together a slide of the I/O just to come to the 66 pins. So that's that there. So as far as the EDSFF interconnect on these 4C and 4C connectors, the beauty here is that we can either plug in media or I/O modules, like a NIC 3.0 potentially, not natively, but what we can do is fundamentally this is designed to support an E3.S format. And so you can see there we've got one module being plugged in into one of the slots, and we've got a cable being plugged into the other slots. So as we've discussed, we need to remove the through holes on that connector, but also the cable shell. They're pretty chunky cable shells we've got today. And so we would like to design the cable shell around the cabled implementations to be sympathetic with the thermal manifold, give us a thermal conduction path, as I'll talk about later, and also have some sort of latch-in mechanism and release mechanism. And equally for the E3S module, we need some sort of latch-in mechanism on there as well. From the thermal management side, we're looking, this is going to be an entirely direct water cooled, and the idea is that we recover all of the energy in the water, and we maintain an output temperature of 65 degrees C for thermal reuse purposes. And so on these lower power modules, we're looking at a conductively cooled path to a local water channel, which is a manifold which carries water nearby. And so we're looking at that. So we want these to be pluggable thermal path to the manifold. So you can see the connectors in gold here are a little bit like an EMC shield connector, but we do need to architect this. How do we get a good thermal connection? How do we apply these? And, because EMC doesn't worry too much about the thermal side of things, but that's, so we need that. And I think the connector guys in the room are probably best equipped to help us do this. And we would attach, for the active cables, instead of these huge QSFP modules, and we're going to OSFP as these things get even faster and more power hungry, with the promise of silicon photonics bringing that energy levels down and low energy chiplet retimers, I'm hoping and thinking that we can be in a 5 watt, and 5 watts would be horrendous to cool in such a tiny connector. But with the water cooling, I'm hoping that we can go to these much smaller connectors and actually cool them. So we need this pluggable thermal path to the manifold to cool active copper and optical cables. I've said it's similar to an EMC gasket, and we need to optimize the design for a low thermal resistance when it's plugged in. I think we, in some ways, depending on how many insertions we can do with these, it's a case of, will this need to be replaceable if you've had too many insertions or something like that? So how do we make this live over a number of insertions? In terms of the E3 module, we're looking at 25 watts and 40 watt cooling capacity. This will only be a single width, short length E3 module, E3.S. But because we've got the direct water cooling, I'm hopeful that we will be able to cool 40 watt modules that are traditionally two slots wide, because the extra slot is used for airflow over fins. So my desire is that we will be able to increase the density to include the 40 watt CXL memory modules, for example. And then I said that I've mentioned the active cable cooling. I'm looking at a 5 watt cooling capacity, and we do that on the EDSF 4C cables and the topology cables. Finally, other considerations. Basically, this module, we in terms of the commercial interest we've got from this, we see this as being used from the data center, and I've presented to Oak Ridge National Labs that have a Frontier supercomputer. So you need 50,000 of these modules based on the way the Frontier is built today to build a Frontier machine. So we would build that in what we call a wall of compute. So there is another interconnect piece there I've not touched on. But we could go to the edge of network. So if you imagine one extreme at the edge of network could be a telecoms box on the side of the road. So you could use these modules inside that. So you need some level of sort of ruggedization. We've got people that are talking about replacing VPX and VME type cards in military systems with this module. So we need to consider ruggedization for mil-aero standards. So the idea is one compute architecture can be used from the data center to the edge and to actually the larger IoT devices. And you don't have to keep reinventing the wheel. And this is all very good from a sustainability. Actually, for those of you that don't know, the entire focus of the re-architecture we're doing here is for sustainability and an energy-centric computing first approach. And finally, that we want to consider some thermal insulation on the module as well. So we want some sort of jacket to go over the whole module, where we can make sure that a minimum amount of the heat, that 65 degrees C water, doesn't go into the air of the data center. It actually gets contained and diverted all into the water. So some sort of insulation, and that could also act as an EMC shield over the modules as well. So some sort of little jacket that you would put over the module. So that's basically the summary. So discuss. So I'll come out now. I'll stop sharing. Okay, did that? So maybe, in fact, maybe if I reshare and just go back to the slides and we can just walk through one at a time. Let me reshare again. So the first one is removing all the pins. Well, so actually, before we do, I'm wondering which is the best way to do this. I probably want to get this keep this high level before we get into the weeds of all of this. Because the idea here would be assuming you know, we're not asking for the impossible here. It's a case of how do we tackle this as a group. And so this work group would work with the experts from the various interconnect companies, and in terms of how do we make this this happen, these changes happen. So that's really my starting point there. So maybe is anybody that's been involved in the other OCP work groups on the interconnect side on how we, you know, any ideas on how we should actually progress this?
Before we get to that, I have a question on the first slide.
The first slide, this one or
the first one?
This one.
Yeah. So you have the components on top, right? IC components on top.
Yes.
And on back is the connectors.
Yes.
So those IC components are like GPUs or CPUs plus some memory or some supporting ICs, right?
Yeah. So well, fundamentally, you have these big power hungry processors, so up to a kilowatt. So effectively, most of this is just power infrastructure in the module itself.
Okay.
On the back, you see some other devices that are scattered between. They're going to be more of the board management control in circuitry there. So that's what we're going to put down there, and that's another work group that I'm setting up on the system management side. So yes, that's.
So yeah, my question is, those will be through BGAs, or it's just use a micro VIA? Because look, in this kind of
everything's, so it'll be an HDI board. Everything will be,
okay.
Yeah, everything will be surface mount. There are no the through holes are just around the edge of the board, as you can see.
Even the ICs is just SMT.
Yes.
Okay.
Yeah, it will be an HDI stack up. It'll be probably a 2 millimeter. The thickness could vary. I would like to keep it as thin as possible, but I'm trying to hit 2 millimeters would be the ideal substrate thickness. Now, by the way, just on that topic, you're seeing these packages become huge, and so we're beginning to ask the question: why don't we just make the these modules also suck up power components like the capacitors into the package, and then they have these horrible solder balls for signal integrity, and so we lose 2 to 5 dB just coming out of the package. So one of the proposals is we actually use this as a chiplet enablement platform. So we actually use the module as a substrate, as an organic substrate that either the interposer substrates can go on, or you can actually put organic chiplets down as well. So that's another step beyond. We're just going to use package parts today, and then we go beyond there.
Thank you.
I guess my first question is a bunch of connector experts. Is this coming and throwing at you has been absolutely crazy and impossible, or fairly straightforward? It just needs time and effort.
Well, how about I think without the through hole it's easier for connector, but the reliability, I don't know. Anybody else can give their comments, because my background is electrical, so mechanically that's my concern.
Right.
Yeah, that's my. I'm trying to. You can go, Z. I'll go after you.
Sorry, Kale. Yeah, you go ahead. Yeah, I can add later. Yeah.
All right. Yeah, I'm trying. In the background, I'm trying to scratch my brain. I think, right. There's a couple from a mechanical perspective, right? There's the retention features, like you see those solder tabs. I think those are probably fixable. My primary concern is the SMT and solderability without alignment posts. So we think of like every SMT connector out there, it has these alignment posts. And as you get to 112 and 200 gig, those SMT tails and the pads on the board get smaller and smaller and smaller, right? So having fine alignment between the connector and what it's getting soldered to is only getting more important. I think figuring out how we align the connector without holes or features on the board is a tough task from a purely, I guess, mechanical perspective.
Is that Kyle speaking?
That's Kyle, yeah, sorry.
Yeah, hey Kyle, thank you. No, so I was chatting to Chris, Chris Blackburn.
Yeah, Chris, yeah, we're on the same team.
Yeah. So the OCP Summit, and one thing, and I used to work. So I was with a company called Nalatech that was acquired by Interconnect Systems. It was acquired by Molex. So I've the Interconnect Systems. We actually did do some interesting frames for putting multiple tiny connectors down, and so it's like, and I was chatting to Chris about that. So what we could do on this top here is potentially we could put an alignment frame during the reflow that these connectors get positioned, and they actually get keyed or aligned. So the replacement of the pips would be that the frame would give that alignment with the module, with some of the holes that are already on the module. And so we would need some sort of frame that would either the connectors could be manufactured and then assembled into a frame, and all of them delivered in a frame that would then be used in the reflow before being released from that, or it's just a separate frame that gets built and the connectors have some sort of features to click into the frame. So that was some of the ideas there that we were hoping that maybe could get over the pip alignment issue. Does that make sense?
Is anybody looking at things like capacitive coupling to avoid having to get copper connection?
That would be a step too far, I think, right now. But fair.
No, we're sort of a bleeding edge chat group. Stuff.
Yeah, no. Well, this I want this to be a reality in like, you know.
Well, I mean, people have done capacitive coupling in the past. And then certainly if you're doing stuff in interposers, which are, 40 nanometer, resolution silicon stuff, you can do large arrays of contacts. The question is like,
yeah, that would be changing too many things. We need to work with today's devices, right? So.
Yeah, but people are doing that anyway. It's like, are we doing anything new here, or are we just doing the next generation of the same old connector?
Well, that's basically where we're in that little in between land, to be honest, in my mind. It's people think this is crazy enough without adding layers like that on top, but so we're trying to break down the silos. I think the innovation here is try to stay as standard as we possibly can, but work across the silos that our industry never does. That's what.
Well, they have like other groups doing chiplet stuff. I mean, I'm kind of looking at the chiplet thing and okay, I've got a pile of stuff in an interposer. Can I glue my interposer to a connector like this? I'm not thinking that works well.
Okay.
I mean, if I could get something where I could just like slot my interposer in and it connects capacitively mostly, then that might work. But it's not been addressed that much in the chiplet group. And certainly with the optic stuff, you're wanting different interconnect.
Yeah, I mean, the problem is we need to change too many things. We need to change the way the chips are designed, the way the channels are built. So we got to work with existing silicon with this design. So if somebody comes up with a solution where they've done it on a chiplet and you want a connector.
Well, I mean, I thought we were doing like a bunch of different subgroups here for different things. So.
Well, if you'd like to do another subgroup on capacitive interconnect, I think that would be good. But it's a bit like so the category I would put that in is it's like I've just said, we're going to use packaged parts, but we have an opportunity to get rid of the packaging, make the module the substrate. Whilst I think in collaboration with ODSA, hopefully we will investigate that path But in the meantime, we'll keep a practical head on our shoulders and use the existing packaged devices from AMD, Intel, whoever will supply us, right?
Yeah, I didn't really come to OCP to do what Intel and AMD are doing.
Well, so or any of the beauty of this approach is that any silicon startup doing their own big chip, like a Graphcore, a Sambanova, whoever, can get into a big architecture without having to spend $1 billion of venture capital money to get their entire data center and software stack to begin to compete with NVIDIA. That's the idea. So anyway, so I think we need to break this down into practical approaches, and then the more exotic ones, yeah, we could certainly set up additional work groups to say capacitive coupled interconnect, is that the way forward? But then there's that question versus.
I'm trying to get away from the edge connector. You know, it's
right.
like things have surfaces. Let's use the surfaces more. And I was kind of seeing a problem with one of the OCP presentations on
Okay.
fiber connections, where the getting on and off fiber seemed to be a real problem, physically. So can you skip that?
Okay. Well, I think that might be just a bit too much.
Well, I'm just fishing for anybody else who's interested in discussing that kind of stuff. So.
Okay. So go on.
Yeah, and sorry. So yeah, back to the remove the through hole. Kyle pointed out the alignment post. So I think also on the board lock, and those board lockers, if you look at the 4C plus, the SFF standard, so the board lock has in the middle, board lock is located in the middle, actually option. So it essentially means if the application needs some the mechanical enhancement, then you can use it, right? Otherwise, you can remove it. So I think the same kind of thing. We look at your application, maybe changing from the through hole board lock to SMT is also the application kind of specific. If in the SFF standard, they specify up to like 200 durability cycles. Basically, the connector need to hold up to like a 200 mating cycle. And if the card like 4C plus, the card is pretty heavy, and if the system is not really good aligned, it applies some side force during the insertion.
Right.
Yeah, that will be issue. So what I'm looking at is what is your application specific, right? If you only need 3 mating cycles and you will be good alignment, then I think, yeah, it seemed to me it's possible to change the through hole board lock to SMT, right?
Yeah, so well, actually, so on that alignment and the mechanical, I'm not sure I fully followed you there, but yeah, so the alignment without the pips is how do we get the alignment, and can we have an alignment frame during reflow is a first question. Is that possible?
I'm sorry, I interrupt you. So my alignment is is between your card and the connect when you insert the card to connect, right? So
that alignment. No. So yeah, that's a good point. So here you go. I'll just go into this diagram. This is the thermal manifold. In fact, let me just bring over my 3D model that's now opened. So to give you the bigger picture, this is actually the thermal manifold on the board that gets mounted onto the board. So you can see here that basically, if I turn on the OMI modules, the E3 modules, sorry. So basically you get an alignment guide as the module gets plugged in. I've got this one here. This is a module with the thermal interface on it. So because it was Chris Blackburn gave me the idea that this would be a better approach. We had the thermal gaskets actually in the manifold, but it was better to put them on the modules. So the idea would be is as you insert this module in, you get the alignment. So you wouldn't have any tilting forces that are going to tear the connector off the board, like if it wasn't sort of guided. So that's from a mechanical retention perspective. But obviously we need the alignment of the connectors when they get soldered onto the board. And then we need the alignment of the connector and obviously the alignment of the manifold so that lines up, everything lines up there and what are the tolerances. But we do have a thermal interface here, which is somewhat sprung loaded. Now, I've only got it on the 3 sides. Whether we can actually squeeze in and put some on the back as well, and that would give you some sort of natural compliance alignment with the compression of those thermal interconnect, and that could be before the electrical interconnect actually starts as well. So does that make any sense, or does that enhance the possibilities of what we can do?
Yeah, I think so. So still, I think one thing is needed to look into it is how those the frames like support the card. So the card is pretty heavy. So during the shock vibration test, right, that's like accelerate to 50 G. Those forces are needed to provide to support the card. So some those board locks basically is there for that purpose, right? We don't want to damage the SMT solder joint, and we want to the force relief on those board locks. So if your frames works very well, and if any deviate from the normal position, and the frame will provide the force to control the card position, then I think it has a good chance we can try the SMT, but still, at the end of the day, we needed to do the test, right?
So the latching, actually, the latching is I did highlight that in the presentation. The latching side of things we're not showing any latching of these modules, so we need to include some sort of level of latching features in this. And I'm thinking that we would use this this manifold again. And so, to be clear, we will probably need to do some tweaks of the E3S module standard. In fact, if we just look here, we've got like an extension of the top. This is like a copper conductive lead cooling, which extends beyond the current E3 spec to give you that thermal mate. So there's things like that. So we're going to need. My objective is that we can support E3 modules, the actual PCBs of any existing E3 module, and we just have a modified casing for insertion into this format. That's been the sort of the idea that we're trying to drive. So any additional latching features that we put onto this module design to mate and latch to here, like either it's a simple screw that we can do on these different sides. So the latching mechanism would need to be designed into the manifold as well, and the modules. Would that give you the mechanical? Would that address the mechanical issues you're mentioning? You were mentioning.
Yeah, that's kind of thing I'm looking for. I think it's a good kind of direction. It's but whether it's sufficient enough to remove board lock and replace it with SMT solid tab, or even remove it, then I think still end of the day we need to do the test, right? To
by the way,
the design's good.
Yeah, by the way, the other thing is this thermal insulation stroke EMC jacket. So if you imagine like a top hat that would go over all of this, you know, as a thermal insulation and EMC approach, it would obviously, you know, the cables still need to be released. So you'd need to account for that. But some sort of top hat that you could potentially put on top of this would be another mechanism that we need to think about. Yeah, the cables going, by the way, just for clarity as well, these modules can actually end up being cables as well, right? So if you wanted to connect two modules together with a lot of bandwidth, then you can start to leverage these PCI CXL interconnects.
Yeah, I'm thinking maybe cable is a little bit easier than the module, right? Module is more heavy.
Yes.
Yeah.
We're at the top of the hour. I guess I should have spent more time also just talking about in terms of people that would like to lead and drive this group forward. Is there any volunteers that would like to maybe throw their hat in the ring?
I wanted to, but I travel too much, so I'm not sure I can go to those meetings. How about they put me as an attentive first?
Okay.
Jinhua Chen from Luxshare, yeah.
Okay. All right. Thank you, Jinhua.
I never run any OCP group before, so if any rules, policies, or anything, please let me know.
Yeah. Well, we're a completely open work group at the moment. My plan is to try and keep it that way. And you know, obviously, what we need to do is this is going to be a completely open standard. So obviously, we need to be able to, if whatever we specify on the interconnect, we need to be able to have that completely open.
So what's the scope of the work? It's really write the spec and report to HPC committee and run meetings.
Yeah, we need to turn these concepts and the discussions here into a real spec of this is what we need to do. These are the modifications to an E3 module. This is the modifications to a standard the standard E3 standard EDSFF 4C cable. I guess the other big topic is this topology connector. I've shown this is an MCIO, but MCIO can't get us to the 112 gig speed today, right? So
and you need active.
You know, should we just switch over to somebody else's, like the Samsung or the Molex, a Samtec or the Molex, that can do 112 gig, and then put the PCIe over there? And how do we deal with the impedances? So we've got lesser pin count. Clearly, we want these connectors to be as small as possible. So either I'm assuming we can leverage what's already been done to a greater or lesser extent, and we can put that into the spec, as long as the manufacturer is willing to do the various OCP open licensing, you know, as is done, so that competitors can build the product as well. So we have a bit more of an open ecosystem there. That's really the driver, right, as I see it.
And then I know it's out of our connect, but I'm kind of interested in you're saying the open license. What does that mean? You know, the other committees have a similar license agreement.
Yeah, I think really the MCIO, so the connectors we've got in this module at the moment is the 4C, the EDSFF, and the MCIO, right, which is PCI SIG. I don't know who owns the 4C, the EDSFF ones. I think that's SNIA. But pretty much anyone can make those connectors, and I don't know what level of what level of compatibility is needed. you should be able to plug a TE cable into a Molex 4C connector, I'm assuming. But basically, as long as we're, as long as any features we put into this, like the latching mechanism, needs to work with all of the implementations, right? So we need to write the spec, and the specs need to be open that somebody can. Now, in terms of how that connector is designed, and connector A is got much better signal integrity than connector B because it contains special IP from one of the vendors, then that's fine. That they become a more popular choice because they have better signal integrity, or better mechanical integrity, or more insertions, or whatever the value proposition is from the different manufacturers. So I'm not wanting to reinvent that wheel. It's just obviously these TA1002 and the MCIO are good examples of interconnect that the entire industry can work to. Obviously, does that make sense?
Yeah. So TA102 basically like follows SNIA by law, so it's the render license kind of agreement, right? And is it when
so this is, I should bring an expert in, to be honest. This is where I need help. We want to do as much as we can in the open. We want everybody to be able to make money selling their widgets, and they've got their own special secret sauce that makes theirs better than anyone else's. So we want that, but this basically, the bottom line is we're trying to replace a 1981 IBM PC, which is what we all still build to today. When in reality, if you look at what's going on in the industry, everything's going proprietary. Like NVIDIA have got their DGX. No one can put anyone else's silicon except for NVIDIA's and DGX. Google have their TPU just for them. Tesla have got their Dojo. We've got startups doing their wafer scale stuff. So everyone realizes that the PC architecture is long overdue being updated, but we don't have an open architecture replacement. So this is a proposal to say, let's replace the IBM PC with this approach, is the idea. And so we want to get the same benefits that the PC delivered to our industry for 30 years or 40 years. But we need to upgrade to heterogeneous with much more bisection bandwidth, much better thermal management, and more sustainable and energy-centric first approach.
I think we all agree with that. I think it just needs to be broken down into different groups.
Right.
Especially that EDSFF connector probably needs to get moved to the SFF group because it's a different form, it's a different mounting for the same form factor.
Right.
But the rest of your cables and connectors here, the ones that come off the side, they go to other stuff or whatever, right? Like those probably don't need to go out there if you're, trying to modify those. But that main one in the middle there probably needs to get shifted, to that group.
That's managed by SNIA, is it?
Yeah.
Okay. Yeah. So we'd need to get SNIA on board, right? That's
yeah, because what you're effectively doing is you're just adding an alternate footprint to something that's already standard. That's a standard mating interface.
Right.
And if you really wanted to, you could also add this, this EMI. I don't know what you're calling it, but like, this EMI band or something that's around it, you can add that as an alternate form factor to the SFF standard as well. So both of those could be, added without the need for showing all this other stuff, right? Like, so you don't have to show the frames and all those other things if you don't want to. You're just adding it as an alternate to what's already there.
Right. So OCP is got a very fundamental approach. Like they've just announced a very good partnership with JEDEC in terms of on the chiplet effort. So I think they're collaborating with them. So some of the spec work gets done in OCP, but then it knows it's better, it donates it to the appropriate body. So maybe we can do the modifications here as a work group, and then we offer it into SNIA later, or do we do it from scratch in SNIA, knowing that we're doing this for an OCP project? We can do it either way, I guess. It's whichever works.
Yeah, I mean, you know, usually this would be taken on by like the appropriate host connector vendor who started the connector in the first place, like for example,
Okay.
TE or whatever. You know, they would put forth usually the effort to, you know, work with you and then propose it. That's typically how it's gone in the past, but you know, alternate connector vendors can also get in there if, you know, if they build a license or whatever, as long as they propose it back to the, you know, the original concept creator. But
right.
Either way, I mean, you know.
Well, I guess there's an opportunity there then. So Kyle, if TE led the charge on the EDSFF connectors, there's a question there. Would you be interested in leading the charge on the tweaks that we're looking for here? And I guess Ant Van Al are the MCIO leaders, but that's what we've got in here. Although I guess, you know, can we make that go to 112, 224 gig with this paddle card approach or not? Or are the solutions from others the only real way forward? And do we need to radically look at how to do that?
So I'd say from perspective, right? I think this group, right, would probably want to define what tweaks are needed.
Yeah, I think
we'd have to go look at and then we could circle back, right? Because so it's, as someone said before, right? MCIO is 1002. All of these actually live in SNIA. So anybody could, right? We could do I think of like maybe that there's that PCI extended work group, right? So we could say, hey, here's this requirements that OCP HPC came up with, and we could then take it to a SNIA technical work group meeting, and someone could present it and say, here's the problem statement, here's the changes we want. I think that's capable, right? But then we'd have to pass the mechanical, right? Anything we do, right, we have to have proof that it's correct to put in the spec.
No, excellent. I think that's good. But I think I'm hearing you say it's like we own the whole problem. There's a number of dimensions that are outside of the scope of SNIA in terms of why we're asking for these things, right? So it would be, rather than this is a very much a cartoon thing I've done so far, but with you experts, we can turn this into maybe an OCP type spec that then we could hand over to SNIA to finish off, or at least, you know, so they understand the intent and why we need it, and then it can go more exhaustively into details with all the SNIA rules.
I think that's probably how it would work.
Okay.
That's the optimistic view. Yeah. Now getting
I think there's no harm in if we can work, if this work group can build a spec. If we can work on the specs of these different aspects, then so we get it into the document form, and then it's a little bit easier for someone else to digest, and at least we've done a first pass of the credibility of what we think we're doing with the various experts. And then it's a case of what does SNIA need us to do to make it into a proper SNIA standard, if that's the way. That sounds like a good approach.
Yeah, I think I agree. It's I think first we here maybe need to get the group consensus, right? What to the solution we want.
Right.
Then,
Okay.
Then go to the SNIA, and the PCI SIG or whatever,
All right, look, we're 10 minutes over, so I think that's a good point to end. I think, so this group is, the intent here is to get us up to a spec level, and maybe there's a couple of separate specs for the different aspects. We want to get this into a group agreement across the experts that join this work group, and then we can take it forward to SNIA, and we can agree. And I can talk to OCP as to whether we push it forward as an OCP standard first, submit it, and then it gets handed into SNIA then, or we do it unofficially. So I'll work out the mechanisms after that. But okay, thanks very much, everybody. Is there any last closing comments? And thank you. I think he had to drop. Jinshu was offering to maybe help lead, but anyone else is willing to maybe throw their hat in the ring to drive one of these things forward. It might be good to have a separate person on the different aspects to keep the work manageable. Okay, guys. Well, thank you. I'm wondering, do we want to keep this on to be a fairly rapid clip as we just get our feet wet on this? Is a weekly meeting good to kick us off, or bi-weekly? I think weekly would be good personally, if that's okay with everybody.
I think I'm okay. At least at the beginning, seems a lot to discuss. So.
Yeah. And then maybe we can get, if people can go away and obviously do stuff in the background and start drafting the specs and looking at ideas. Okay. All right. Thank you, everybody. Well, feel free as well to ping me if you've got any additional ideas. And yeah, so I think next week is really trying to maybe just define what specs we're gonna create, and if we can get some activity going on each of those in the background between meetings, then that'll be great. Okay, thank you all. Stop sharing.
Thank you, sir.
Thank you.
Thank you.
Bye.
Thank you, bye.
Bye-bye.